Okay, welcome back, my dear students. In the last class, we have discussed about the geometrical isomerism, especially its naming, EZ notation. I think you might have studied it well. Next, we are going to discuss about the properties of geometrical isomerism. It's very simple. First property is melting point. We know that trans isomer is more symmetrical than cis isomer. For example, malic acid. This is fumaric acid. I think it is on the opposite way. That is, it is a trans isomer. Fumaric acid is trans isomer. COIS groups are on the opposite side. In malic acid, COIS group are on the same side. Okay, in trans isomer, we know that it is more symmetrical. For example, if we consider a point here, if we draw a line from here, we can meet a COIs, and extending this line to the other direction, we can make the same COIs. That means this molecule has a center of symmetry. That means trans isomer is more symmetrical than the cis isomer. Therefore, in the crystal structure, trans is more closely or more effectively packed. Therefore, intermolecular force of attraction will be stronger in trans isomer in the solid state compared to cis isomer. Therefore, the melting point of trans isomer will be higher than cis isomer. Consider here the melting point of malic acid is 403 Kelvin, whereas in the case of fumaric acid, that is trans isomer, it is 559 Kelvin. It is higher. Okay, that is the first point. Trans isomer is more symmetrical, so more strongly packed in the crystal. Therefore, its melting point is higher. Okay, that is first property. And next property is dipole moment. Dipole moment. And here we can see that we consider 1,2-dichloroethene cis isomer and trans 1,2-dichloroethene. We know that dipole moment, we know that is a vector quantity. In the case of cis isomer, the CCl bond dipole vector is in this direction and this CCl bond vector is in this direction. That is almost the same direction. So they are added up. So in the cis isomer, the dipole vectors are in the same direction. So they are added up. They have a higher dipole moment. Here dipole moment is 1.8 dpi. Whereas in the trans isomer, this CCl bond vector is in this direction and the vector of dipole moment of this CCl bond is in the opposite direction. They are mutually opposite, therefore they cancelled each other. Therefore, dipole moment of trans isomer in this case is 0 dpi. Okay, in this case, that is dipole moment of cis isomer is higher because dipole vectors are same direction, so they are added up. Whereas dipole moment vectors of trans is very low or 0 because vectors are opposite direction, so they are cancelled. And that is the second point, second property. And third property is solubility. Whether cis isomer is poorly packed in the crystal, therefore its lattice enthalpy will be lower. It can be easily breaked and it has higher polarity. Dipole moment cis isomer has higher value. Therefore, cis isomer is more soluble in polar solvents like water. Cis isomer is more soluble in polar solvents like water. For example, solubility of malic acid. Malic acid is a cis isomer. It is 79 gram per 100 ml. Whereas solubility of fumaric acid, that is a trans isomer, it is 0.7 gram per 100, very low value. So solubility of cis isomer is higher due to poorly packed in the crystal and high polarity. Okay, and fourth property E is ease of cyclisation. Ease of cyclisation. That is cis isomer. There is a higher chance of being cyclized or forming a ring. For example, malic acid, when heated about 423 Kelvin, it loses water molecule and it cyclizes to form a cyclic ring called malic anhydride. Whereas in the trans isomer, the COH groups are on the opposite side, it is very difficult to cyclization. But even heating at a very high temperature, it is first converted into cis isomer. In the trans form, it cannot form cyclic ring because these are in the opposite direction, cannot form a cyclic ring. But at a higher temperature, this is converted to cis form, so it can form. Here also we get malic anhydride. No fumaric anhydride exists. Fumaric anhydride does not exist. This also we get malic anhydride. Okay, that is, it first converted into malic acid, then cyclized to form malic anhydride. And there is a fourth property. And next, sixth property is heat of hydrogenation. Fifth property, heat of hydrogenation. We know that heat of hydrogenation or enthalpy of hydrogenation is the enthalpy change accompanying the hydrogenation of 1 mole of an unsaturated compound. Okay, that is when an unsaturated compound is added to hydrogen, it becomes saturated. During this process, heat is liberated, enthalpy change occurs, and that is called the heat of hydrogenation. The more negative the value of heat of hydrogenation, that is delta H hydrogenation of an alkene, the less stable it is. Okay, more negative value of enthalpy of hydrogenation means it has a higher tendency to undergo hydrogenation. That means it is less stable. Okay, the more stable has a lesser tendency to add hydrogen than the less stable compound. More the negative value, enthalpy of hydrogen is negative, more negative value of delta H hydrogenation of an alkene means less stable. Okay, trans isomer is more stable due to less steric strain. In the trans isomer, the groups are in the opposite direction. Therefore, there is a less steric strain than cis. Therefore, heat of hydrogenation of trans is less negative than cis isomer. Heat of hydrogenation of trans is less negative than cis isomer. For example, consider this reaction. It is but2ene, adding hydrogen in presence of platinum. We get butane. Okay, delta H hydrogenation, we are given this minus x kilojoule. For cis but2ene, the x is equal to minus 120 kilojoule. For trans but2ene, the x is equal to minus 116. That is, heat of hydrogenation of cis is higher because cis is less stable than the trans isomer. And these are the main properties of geometrical isomerism. Actually, these properties are used to distinguish between the geometrical isomers, cis and trans isomers. Okay. Next, we are going to discuss about the last section of this chapter, that is geometrical isomerism in oximes. Actually, oximes are the compounds containing C double bond NOH group. C double bond NOH group. It is actually formed by the reaction between the hydroxylamines with aldehydes and ketone. We know that hydroxylamine is actually NH2OH. It is when react with aldehydes or ketones. For example, if we consider an aldehyde, RCHO, then here this HOH, not in this way, in the other way, that is NH2OH, that is hydroxylamine, react with an aldehyde, RCHO. Then this H2O eliminated, we get RCH double bond NOH, that are an oxime. Okay, Oximes are two types, aldoximes and ketoximes. Aldoximes is the oxime of an aldehyde. That is, aldehyde react with hydroxylamine, we get aldoxime. And a ketone when react with hydroxylamine, that is in this way, that is it is a ketone, RCOR dash, react with hydroxylamine, NH2OH. Then water molecule is eliminated. We get this compound, RCR dash double bond NOH, that is ketoxime. And the aldoxime and ketoxime, both carbon and nitrogen are sp2 hybridized, and the compound is planar. Okay. And the third sp2 orbital of nitrogen contains a lone pair. The nitrogen is sp2 hybridized. One sp2 orbital forms bond with OH group. Another sp2 orbital bond with carbon, sigma bond with carbon. And the third sp2 orbital contains a lone pair. Here also third sp2 orbital contains a lone pair. Okay. Then aldoxine ketoxime can show geometrical isomerism due to the restricted rotation of C double bond N. Similar to C double bond C double bond N is also rotation is restricted. We already know that pi bond rotation is restricted. Here one sigma bond, other is pi, therefore rotation restricted. So it can show geometrical isomerism. But here naming is not cis and trans. Actually here naming is syn and anti. Okay, for cis we are using syn, for trans we are using anti. For aldoximes, H and OH same side is called syn. And when H and OH are on the opposite side, it is called anti. For example, in this case, it's an aldoxime. This H and OH are on the same side. It is called syn isomer. And it is another aldoxime. Here H and OH are on the opposite side. It is called anti. And for ketoximes, the syn isomer is the one in which the first named alkyl group, that is alphabetically first alkyl group and OH same side, is called syn. And the first named alkyl group, that is alphabetically first alkyl group and OH are on the opposite side, it is called anti. Consider this example. This example, this is an aldoxime. This we already discussed. H and OH same side, it is syn. H and OH opposite side, anti. It is syn acetaldoxime. It is anti-acetaldoxime. Ketoxime example is here. Here one is CH3, another is C2H5. Okay. Here C2H5 is ethyl, it is methyl. Alphabetically first one is C2H5. But this C2H5 and OH same side. It is called syn isomer. It is syn. Here the alphabetically first group, that is ethyl group, and OH are on the opposite side, therefore it is anti-isomer. Okay, very simple. Okay, I think you almost you might have understand all these things. Our chapter is stereochemistry is over. You study well your textbook and prepare for the examination. Okay, thank you.